Next, I'm pleased to introduce Dr. Jade Benjamin-Chung. She is a research scientist in the Division of Epidemiology and Biostatistics at UC Berkeley. She completed her PhD in epidemiology and her master's in biostatistics here at UC Berkeley also. And as we'll hear a bit about this morning, her research applies cutting-edge causal inference and machine learning techniques to study infectious disease interventions in the US and internationally. Welcome.
Thanks very much for having me. I'm really excited to be here. And my research really lies at the intersection between a few different disciplines: public health, epidemiology and biostatistics, which is what I'm trained in, and then also data science, our theme today. And my research spans a wide range of topics in infectious disease as well as child growth and development. But today I'm going to focus on one of my studies in particular and highlight how we've used data science in that particular study. So respiratory viruses are big in the news right now. You've probably all been reading about coronavirus. Based on the information we have as of right now, though, many argue that influenza is something we should be much more concerned about because we are in the midst of flu season, and flu impacts a really large number of people every year. So one of the studies I've led over the last several years has been focused on evaluating a program called Shu the Flu that's offered here in Oakland, California. And it's targeting kids. So kids are actually well known as super spreaders of the flu. This is because, as you can imagine, they might not have the best hygiene, right? Maybe they're not able to avoid touching their face, as was recommended at the beginning of the conference today. And they're also clustered, right? They're spending all day together at school with that poor hygiene practice. And so they really are responsible for the majority of influenza transmission. And so the idea is, there's been lots of work that suggested if we could get more kids to get the seasonal flu vaccine every year through something called herd immunity, we could actually get, if we reach a high enough level of vaccine coverage, we could interrupt community-wide flu transmission. And this is really important for really young children, infants, and for older people who have lower immunity and may or may not be able to be vaccinated themselves. So the goal of Shu the Flu, and this is a picture of one of the Shu the Flu clinics, was to provide free flu shots to all elementary schools in the city of Oakland. So this is public, private, and charter schools starting in 2014. And here we can see all the kids lining up to submit their consent form and get their shot. And we have been measuring the impact not only in kids, but also in the community here in the Bay Area. So I want to talk about how these different pieces fit together in this particular study and more broadly. So we can think of public health as sort of motivating the question, right? So we're asking, does offering free flu shots to elementary school kids interrupt flu transmission community-wide? Then there's the epidemiology and biostatistics piece. So the epidemiology piece helps us figure out what study design we should use to collect really good, minimally biased data to hopefully allow us to make causal inferences about the effect this program has in this particular community. And then the statistics part is really important because we have to know what kind of model we want to use. And I won't go into the details, but here we're using something called a difference in difference type analysis, which was appropriate for this particular setting. So what does the data science piece contribute? Well, for this study, it's helping us create a reproducible workflow, and I'll come back and define what that is in a little bit, and we're using a variety of tools to do this. R, GitHub, Docker, Amazon Web Services, and Slack for the kind of communication side. Thinking about this more generally, we can think of the public health angle as helping us choose what we want to eat. What dish do we want to make? The epidemiology and biostatistics piece helps us decide what recipe we want to use to make that particular dish and what ingredients we need. And where data science comes in is it gives us the tools that we need to successfully make that recipe and recreate that dish. So for example, if we don't have the right pot or pan or a really dull knife instead of a nice sharp knife, we're not going to be able to accurately reproduce the particular dish we have with the recipe that we have. And also, data science comes in when we think about efficiency. So if I want to make a bunch of cookies, if I have a stand mixer that I can use to sort of make my whole batch of dough versus just a spoon or, God forbid, just my hands to mix all those cookies, we're going to do a lot better if we have a stand mixer, right? And so what I'm going to talk about today is this data science piece and how we can kind of move from the hands to the spoon towards the stand mixer in the field of public health. And a running theme that I'll talk about is something that we call the reproducibility crisis. How many people here have heard this term? Okay, good, great. So there's sort of increasing widespread recognition that many key findings that are in the published literature have not been able to be reproduced. It kind of started in psychology, and now we see documentation of this in economics, basic science, in my discipline, in clinical research. It's really, really widespread. Nature did this survey, published it in 2016. On this pie chart here, the red portion indicates that really the vast majority of scientists surveyed agreed that there's either a crisis or a significant crisis, and that we need to do something about it. So what contributes to our kind of failures to reproduce key findings? Well, there's several different key cognitive fallacies, and I want to make the case that these are things that are really kind of human nature, and we probably should be embracing them and coming up with tools that minimize them rather than pretend like we can actually get rid of these things. So what are these fallacies? Well, to start, we have hypothesis myopia, meaning we as humans tend to sort of define our hypothesis, and then we set out and collect data, collect evidence, and interpret our evidence in a way that's biased towards sort of showing that our hypothesis was right, rather than refuting it. Again, this is just sort of how we are as humans, but it can lead us towards this reproducibility crisis. We also have a tendency to see patterns in the data and interpret them as meaningful when they could be random. We do something that I'm calling asymmetric error checking, where if we analyze our data, we get a certain finding and it's concordant with expectation, we might just sort of check it lightly and move on. But if we get a really weird finding, like if I found that this program really increased transmission of flu, I would really scratch my head and wonder, did I make a really bad coding mistake here, or did I do the wrong kind of model? And so that kind of imbalance in how we check for errors can also contribute to reproducibility failures. And finally, as humans, we're just really good at crafting stories to explain any answer, any finding that we have. A lot of this has to do with incentives for scientists, right? So if we want to advance our career and keep our job, we have to publish in good journals. Really good journals, at least in my field, tend to like to publish things that really sort of advance science, not null findings or contradictory findings or unexpected findings. And so until we sort of change incentives, that practice is probably not going anywhere. So while data science can't fix all of these issues, it certainly can contribute to some of them. And so I'm going to talk about how in my work I've used data science to try to protect against these natural human instincts, these cognitive fallacies that contribute to lower reproducibility. Here's the traditional scientific process we're all familiar with. We define a hypothesis, we collect data, analyze it, we publish. I want to talk about some new additions to this process that I'm hoping become a lot more commonplace as we move forward. Some of them are related to data science, some are not, but they all fall into this movement to increase reproducibility. So here we have, in between defining our hypothesis and collecting data, this practice that in my field is becoming increasingly common and is required by many journals now, which is study registration and publishing protocols and pre-analysis plans. So this basically says, particularly for things like clinical trials, if I'm going to go out and collect human data and spend millions of dollars to conduct a study, I need to say upfront what my hypotheses are, who I'm collecting the data in. I need to put that out there so that if I do all that work and I get a null finding or a finding that's hard to get published, that can at least be known that I was going to do that. And it's really helpful for reducing publication bias. It also kind of forces us to be way more honest when we go to publish our results about how we deviated from the original plan. It's natural and okay to deviate if you need to, especially when it's well justified, but it's important to be honest about what we said we were going to do versus what we actually did. Next is creating a reproducible workflow, and that happens in the data analysis phase. I'll spend a little time on that and come back to that in a moment. Internal replication, which is a process that we've used in my lab to basically reduce error in our coding process as much as possible before publication. Publishing code and data to allow scientists and others in the community to reproduce our findings and to build upon our work as efficiently as possible. That usually happens along with publishing our manuscripts. And then finally, I'm not going to go into this today, but in my discipline at least, there's an increasing practice that I'm calling external replication, where I publish my paper, hopefully I put my data and code out there. Someone from a different group, independent from mine, comes along and they say, I want to check your work. I want to make sure I can get the same answer when I work with the data that you have. And so there have been some very, very high-profile cases of of studies that were really seminal in their field. Other people came along, did this external replication, and were not able to fully reproduce the original findings. Okay, so I'm going to first talk about creating reproducible workflows. So the dream is that we could press a button or click our mouse once, hopefully, and reproduce everything in our published paper, every number, every figure, every table. That's the ideal, and ideally we could do this on any machine. We could do this today or in 20 years and get the same answer. Now, unfortunately, in my particular discipline, the reality is very far from this for many people. And for me, until starting to incorporate more data science techniques into my work, the reality was far as well. So what we often see is that there's many versions of data and code, but there's not great version control. So it's hard to kind of know what the latest, most correct version is, or to go back in time if you need to kind of correct things. Often code is very obtuse and poorly documented. This means that maybe someone in my lab might not even be able to easily understand a particular script, and then when I go and publish it, other scientists, even though it's out there, won't be able to easily use it. This leads to these reproducibility failures. So if code is not clearly documented, doesn't have a clear overall architecture, and then you go and publish it, someone who tries to reproduce it won't be able to, especially if they're on a different computer, if it's 5 years from the original publication, perhaps after they've updated their software. Perhaps I update my software and I can't replicate something that I did 5 years ago. And finally, many times data and code are not published. So these are all things that we can fairly easily address. And we've done this through a really amazing team of students here at Berkeley. I've been working with students in computer science and in data science who are either double majors in public health or are really interested in public health or medicine. And they've been just a really awesome team. They've introduced all kinds of innovations from their disciplinary training that we are now using in our work. So we're using Slack, we're using Github to keep track of our versions of our code. We're introducing unit testing, which is not something that's really traditionally been done in my field. We built a HIPAA-compliant Amazon Web Service computing platform, which I'll come back and talk about. We're using Docker, which helps us create a container that has the exact version of software and exact software itself that we used in a particular analysis. And all of this has been put into a data science-oriented lab manual, which is really not common, again, in my discipline for more statistically oriented research studies that don't have a wet lab, for example. So this is publicly up on GitHub, and here's a screenshot from it. We basically have standardized how we organize our scripts across all our studies, and we've given guidance so that any new member of the lab or any collaborator can come in and quickly understand how we organize things. And also, if you wanted to replicate, one of our findings using the public data and public scripts that we have, it makes it really easy to understand how we've set everything up. And this is a sort of living document that we update as we go, and we're constantly fine-tuning it. Oops. So to come back to this flu study, here's a picture of the Bay Area. In Oakland here, all these dots are different schools where we collected data as part of our evaluation of the Shu the Flu program. We enrolled schools up in the West Contra Costa Unified School District, which is sort of in the city of Richmond area, and we identified that through a matching process as a very similar district to Oakland Unified. This program has vaccinated up to 10,000 elementary school children every year in Oakland, so it's very large in size. And we have a really wide range of different types of data and large volumes of data for human studies at least. So we collected surveys to measure influenza vaccination practices on over 6,000 students. We partnered with the school districts to collect absence records because when students truly have influenza as opposed to a different viral respiratory infection, they tend to miss school because they're very severely ill. So we've got over 31 million student days of data on their absences over 6 years. And we have community influenza hospitalization records on almost 3 million individuals. And then finally, we've partnered with Kaiser, and they've shared 6 years of patient data with us, over 57 million person weeks. So this is a very large database. And we're working with them using some machine learning algorithms to use their patient data to understand the impact of this program as well. So Kaiser is very protective of their patient data, which is an important, great thing. And in order to have access to their data off the Kaiser campus, we had to agree to a pretty rigorous data use agreement that required us to build a HIPAA-compliant cloud computing system. So for those of you who don't know what HIPAA is, it's basically a policy that requires us to do everything we can to protect patient privacy and confidentiality when working with their data. And so, in the school public health, we didn't already have that kind of infrastructure. Believe it or not, there are very few studies that require that exact sort of setup to do their analyses. So we partnered with one of my students who's trained in computer science and also in public health, and we partnered with Research IT here at Berkeley. It took us about a year to kind of figure out the architecture of this system and to work with folks at AWS to get it up and running. And it's a really awesome resource. It's sort of serving as a template now for many other groups around campus. It allows me, someone who's not a computer scientist, to log on and see RStudio Cloud, which is a cloud-based version of what I would normally use on my desktop or my laptop. And the beautiful thing about Amazon Web Services, for those who haven't used it before, is that I can choose whatever kind of machine I want that day. So if I'm doing something kind of light, I can choose a really cheap instance. If I'm doing some machine learning with cross-validation, I can choose a machine that can handle that with my 57 million person weeks of data and do it very efficiently and very quickly. So we've been really pleased with how this has turned out. Here's a screenshot of our public GitHub repository for one of the aspects of this study. This is our surveillance data on community-wide influenza hospitalization. I'm not going to show all of these to you, but the cool thing is for each component, they're all organized the exact same way. So if someone really wanted to come along and look at what we did and reproduce it or build upon it, it would be really easy once they learned how one of them was set up to use any of them. And now I'd like to touch on this internal replication process that we've built. And again, the purpose of this is to try to reduce errors before publication. So any given paper we publish probably has thousands and thousands of lines of code that were used or written in order to get our results. And it's just inevitable that there's probably going to be a mistake somewhere in there. And so we've come up with this process, and it's used in other disciplines as well, but it's not commonplace in my field, where we have at least 2 analysts from our team internally. And at the beginning, we review our analysis plan. Usually we pre-specify and register that online. We document any changes we need to make to it, perhaps if the data changed unexpectedly. And then we separately work to create our analysis data sets. So we do our data cleaning. We take our raw data, we get it into the format we need for analysis. Do it totally separately, having no conversations with each other. And in the case of a randomized trial, which we've analyzed with this method, we actually blind ourselves to treatment in the data sets. We don't know the true treatment and control groups. And then we come back together and compare until the data sets are functionally identical. This is, believe it or not, actually quite difficult to do, to get them to be really, truly functionally identical. Same number of rows, same values, same distributions in every single column. Then after that's achieved, we move on and we conduct our statistical analysis. And this is usually broken up into a bunch of different steps. And we do that separately and compare and revise until we've replicated. And we usually pick sort of a tolerance level of 0.001, meaning we take every matrix that we generate in the statistical analysis, take the difference between them, and we want every single cell and every single matrix to have a difference that's no bigger than 0.001, which is the threshold that would affect the number you see in a final publication. So I've done this about 4 or 5 times now with other analysts, and it was a sort of illuminating and terrifying experience because it made me realize that no matter who I was working with, we always had at least a few little errors. They didn't always impact the final result, but they were there and they needed to be addressed. And there were tons of little judgment calls when you're working with real data that you have to make, how you handled that missing value, how you merged data that doesn't really cleanly merge, right? So there's all kinds of ways that we can sort of stray from the original analysis plan, and typically those things are just sort of happening under the hood and they're not well documented. And by using this process, we were really able to bring all of those things to light, make sure we were making decisions that we both agreed on, or sometimes we'd bring in a third person to make sure we're all on the same page. And if I had the resources, I would do this in every single study, but it is very resource intensive. And so now what we usually do is, depending on resources, we'll pick the part of our analysis that we think is most error prone, and at minimum, we will try to do this for that, if not for the whole thing. And then finally, just to briefly touch on the fact that we publish our code and data as much as possible. And I'm a big fan of Open Science Framework. There's lots of other platforms for this, like Dryad, for example. I like Open Science Framework because it has a pretty user-friendly interface. It allows me to, for example, for this flu project, I've got different components that will eventually lead to different scientific papers. I've integrated it with all the different GitHub repositories for this particular study, and then the data that we're allowed to share will also be available all in one place. And so the GitHub repositories get updated live if we have to make changes to them, and the data can be versioned, and all documents can be versioned as well. And so we really like this platform. And then to close, I just wanted to briefly touch on how we're preparing the next generation through teaching. So in the Division of Epidemiology and Biostatistics about 2 years ago, we started to try to incorporate R training into most of our epi-biostat courses. So it used to be sort of separate, or they were using other software like Stata, for example. And R has really come up with amazing teaching resources and sort of cloud-friendly resources. And so we've sort of made a decision to try to incorporate R specifically into as many courses as possible. And we no longer have a computer lab, so this all needs to be done in the cloud. You need to be able to do it on any laptop in any physical space. And so what we've done is we've made a series of online R tutorials that are really geared towards our epidemiology curriculum. And so what we can see here is a student is accessing this on the web, they're reading about some new concepts, and then they have these interactive coding blocks where they can practice and check their work. We've also adopted some tools and adapted them that were used in Data 8. I think many of you in this room have either taken it or familiar with what it is. So Data 8 teaches Python, and it has a really great auto-grading platform. This did not exist for R, so we created it for R. Basically what this means is that when a student is working on a problem, this is in an RStudio interface, they can run a line of code that says check problem 1, and if their answer is right or wrong, they will get customized feedback depending on what the value of that particular object is, and they'll sort of know what they should try next if the answer was wrong. And we're also using our Data Hub at Berkeley, which is a similar platform to what's used in Data 8. It allows students to do all of this on the web without having to have a specific type of machine or computer. And also, I'll just mention, all of this is open source, so if anyone here is teaching R and wants to use the autograder, I would love for you to adopt it. Happy to chat about that. And then all of this is integrated with 2 other teaching platforms here at Berkeley that were developed here at Berkeley, Gradescope, which is an amazing resource for grading, and then OKPy, which is the server that we use for our auto grading as well. Thanks, I'll take questions and comments. Yes. Oh yeah, microphone.
It was a really cool talk, so thank you for that. In this work you did with Kaiser, where you had to set up your own or have access to a HIPAA compliant cluster, you mentioned earlier in the talk that the work that you all were doing has been containerized and is reproducible, and containers also let things be portable. So I've heard about this idea of like data visitation. So you don't actually need to ever share the data with other people, but you can let people visit your data with, not people visiting it, but let their code visit the data.
Yeah.
So like if you could have actually shipped your containerized workflow to the data and gotten the results back from that analysis, would that have been sufficient for what you were doing? Because I've heard this idea talked about, and I just wonder, and this is...
Yeah, that would be amazing if we could do that. I suspect that our data use agreement, as it currently stands, would actually not support that. So unfortunately, the Kaiser patient data is not data that we can share in any format. And I think that even running someone else's code on it would require probably a whole new type of...
I meant your code. I wasn't
Our
actually
code.
like volunteering. Like,
Oh, yeah.
My own, yeah, but like for yours, instead of actually moving the analysis to AWS or whatever, like if Kaiser had the data stood up, so in principle, you could have sent them your workflow, it could have gotten executed, and you could have gotten the answers back, and then you never would have actually needed to look at the data.
They offer that if you code in SAS. And so, yeah.
Sweet. Oh, great.
Right. So I was like, well, that's not going to work for us. All the machine learning libraries we use are in R or Python, right? So it would require them on their end to have that capacity, which unfortunately that's just not what they use. So I think it's a really great idea, and I bet there's a lot of other use cases for it. But I do like this idea in general, and I think it could be a great model for the future.
it just feels like that's where things are going to move because, as somebody pointed out, there's just too much data to replicate it all over the place. But
Agreed. Yes.
Hello? Okay. Thank you for this great talk. My question is a little bit more broad at going towards the reproducibility component. There's a stereotype out there that scientists make terrible programmers. And so this is really cool to see how moving scientists towards making better code and making better programs that other people can access. And you gave like some really cool examples of what your team has done for a scientist or someone in data science who is thinking about this reproducibility issue. How did you decide on what you were going to do in terms of your use of GitHub, and what would you recommend for someone who's like never thought about this before in terms of sharing their code with others in a very clean and maintainable way?
It's a great question. I think that we have to start training our students from the very beginning in these practices, because I think there's a bit of a culture, especially among female students and scientists, that coding is hard, and if you don't learn it from the beginning, it's hard to adopt later, right? I didn't think many years ago when I got into this line of work that I would code as much as I do. I code almost every day. I had no idea. I thought I would be doing statistics or writing or something like that. But coding is a huge part of what I do. And yeah, I think it just has to become part of the standard curriculum so that it's not seen necessarily as a separate tool. Now, there's of course situations where I hire someone to do a more specific coding application that's just well beyond my particular skill set, and I think that will always be the case. We might want to outsource things to programmers in certain cases, but at least in epidemiology and biostatistics, I think that's the direction we're moving in, is that students will learn GitHub, in their basic epi biostat courses, and that will just kind of become part of the common set of standard skills.
I think for time we do have to move forward. Thank you so much, Jade. That was really helpful.